So we also have Pythagorean identities for hyperbolic functions of complex numbers. So we are to start with this form. Take note, when we try to look at the perspective of real numbers, when we return to that, the square of cosine theta plus the square of sine theta, or of course you can commute that, you can start with sine and cosine, is actually equal to 1. Again, it's the sum. Similarly, if we're talking about trigonometric functions for complex numbers, the cosine or the square of the cosine z plus the square of sine z are again just rearranging that because it's addition is commutative, it's still equal to 1. But when we reach hyperbolic function, the identity becomes 1 if we're going to subtract the squares of both. Okay, and it should be this process, the square of the hyperbolic of cosine z minus the square of the hyperbolic function of sine z. It should not be commuted because it's subtraction. Okay, so we're going to show that this is true for hyperbolic function, unlike this one here, which actually pluses. Okay, so first, let's try to provide the forms for our hyperbolic function of cosine and sine, so that we will be guided with our process later. For our hyperbolic function of cosine z, it's actually equivalent to e to the power of z plus e to the power of minus z all over 2. That's for the hyperbolic function of cosine. For our sine, okay, you still have e to the power of z, but we have minus e to the power of negative z still all over 2. So we're going to show that the square of this, when added, will result to 1. Okay, so we would start with the proof. So we have here the square of our hyperbolic function cosine minus the square of the hyperbolic sine function must be equal to 1. Okay, so we need to reach 1 there, so we will have that at our final part. This is equivalent to, we can write it this manner, the hyperbolic function of z, and you have the square here, minus the hyperbolic function of sine h, and you have here square. Okay, so that's what it means, right? When you say a square of a hyperbolic or a trigonometric function. Now we're doing this because this is the equivalent for these functions, and we need to square it later on. So this is equivalent to this form for the hyperbolic function of cosine, e to the power of z plus e to the power of negative z all over 2. You're going to square that, minus e to the power of z minus e to the power of negative z, okay, over 2. You're going to square that as well. Now for this, we need to show that again this would be equivalent to 1. So what we need to do here is to apply the rules of exponents and later on combination of fractions or rational expression. Allow me to use first the power law of exponent, sharing it to this binomial and denominator, similar to this as well. So only for the binomial in the meantime, let's try to simplify them later on. So you have your e to the power of z plus e to the power of negative z, the square of that over your 4, because that's the square of 2, right? Minus, you will have your e to the power of z minus e to the power of negative z over 4 as well. So you're going to square our numerator. Now, obviously, we have the same denominator of 4, but let's try to combine them later, okay, as soon as we expand both binomial expressions that are being squared. So when we square a binomial expression, please don't forget, you have here the square of the first term plus twice the product of the first and the second terms, and plus the square of our second term. That's for the first group. Minus, again, let's try to simplify first this one because the negative sign here will mean very important as we also combine them later on, because we have a grouping symbol here, the square of the first term minus twice e square, e to the power of z, and then you have your e to the power of negative z, and you have here plus the square of you have your second term, okay, over 4 as well. Okay, this time let's try to combine the exponents, power law, multiplication law, power law, or you can say power law, product rule, power law. Okay, you can also use those terms. So you have your e to the power of 2z plus 2, that's e to the power of 0, right? Because that's z minus z. Then you have here plus e to the power of negative 2z all over 4. Then the second one, minus e to the power of 2z minus 2 e to the power of 0 plus e to the power of negative 2z still all over 4. Now that all the terms now are without grouping symbols for both two terms, we can now actually combine them into one expression. But please take note of this. Our denominator is still 4. When you have here e to the power of 2z plus 2, that's actually e to the power of 0 is equal to 1, similar to that. So that's why we only have 2 plus e to the power of minus 2z. But for the second group, take note, we have here minus. It's actually minus e to the power of 2z, the grouping symbol, minus 2 times 1 or 2, plus e to the power of negative 2z. I'm writing it that way so that later on, we can, of course, okay, apply the distributive property here as well. So we need another step. Of course, you can shortcut your steps if you would like to, but I'm going to present it here anyway to show the final form. Plus 2 plus e to the power of negative 2z. The next term would become minus e to the power of 2z. This becomes plus 4 by distributing the negative sign. And finally, minus e to the power of negative 2z. All over 4. Sorry, plus 2 rather. Plus 2, my bad. Okay, now this time, we can see terms that are actually opposites. E to the power of 2z, and we have minus e to the power of 2z. So with that, that's actually 0. Similarly, e to the power of negative 2z and negative e to the power of 2z are also opposite terms. You can cancel that. So what remains on our numerator is just simply 2 plus 2 over 4, or actually 4 over 4, which gives us 1. This is our target, right? To show that the square, and the difference of the squares, where we start with hyperbolic function of cosine, and the second is hyperbolic function of sine, will result to 1. So with this, we have shown that the square of the hyperbolic function of z, okay, minus the square of the hyperbolic function of sine z is equal to 1. This is the proof of the given identity. Okay, so hopefully this is clear, and you can always try to review this on your own time. Thank you very much for watching.